Good morning to everybody. Good afternoon and good night to all over the world. Today, this is my fourth class, and this is the topics of Physics 1, another new chapter, Elasticity. In this lecture, we will discuss about the what is elasticity with examples and different types of elasticity and Hooke's law, moduli of elasticity, Poisson's ratio, relation between elastic constant and their determination, and Cantilever, some of real examples we'll try to solve connecting with this chapter, elasticity. So welcome to everybody in this lecture. So first of all, what is elasticity in our real life? The property of a body by virtue of which body regains its original size and shape with the applied force is removed is known as elasticity, and the body is known as elastic body. Suppose, for example, spring, rubber, skin, etc. And this is actually in our real life we use the elastic body. So this is the rubber. Elasticity means actually স্থিতিস্থাপকতা। তো এখানে রাবারটা কিন্তু একটা স্থিতিস্থাপক বস্তু, যেটা আমরা ফোর্স দিলে কিন্তু অনেক বড় হয়ে যায়, অনেক ল্যান্ড বৃদ্ধি পায়, এবং আবার ফোর্সটা নিয়ে ফেললে আগের জায়গায় ফিরে আসে। এই ধরনের বস্তুকে বলা হলো স্থিতিস্থাপক বস্তু। নাও another one is plasticity. What is plasticity? The property of a body by virtue of which body does not regain its original size and shape when the applied force is removed is known as plasticity. The plastic body, plastic paper, clay, putty, etc. This is actually plasticity, for example. And the rigidity, what? The property of a body by virtue of which body does not change its original size and shape when the force is applied is known as rigidity. Suppose wall, blackboard, duster, etc. is the actually rigidity. That means elasticity does not work. Now, due to given force, we have to use the stress and strain. Okay. This is also an example of elasticity, and this is the jumping. Utilize a long elastic strap which stretches until it reaches maximum length that is proportional to the weight of the jumper. The elasticity of the strap determines the amplitudes of the resulting vibration. This is actually a real life example of elasticity. So now, after completion of this module, we should be able to demonstrate your understanding about the elasticity, elastic limits, stress, strain, and ultimate strength. Then write the apply formula for calculating Young's modulus, shear modulus, and bulk modulus, and solve problem involving each of the parameters in this above objects. Now, first of all, what is an elastic body? An elastic body is one that returns to its original shape after deformation. That means after applying force and removing force, we'll get the original body. So this is the golf ball, and this is the rubber band we have used to determine the elastic body, and this is saucer ball. So the ball, if we kick the ball, then the ball will get, after applying the force, and when it will go in the high of the sky, then the force is removed. So we get the original shape of the ball. Then this is the elastic matter. Now, an inelastic body, that means plastic body, is one that does not return to its original shape after deformation. Suppose bread, if we cut the bread, will not get the actually previous deformation. And clay also, if we make a statue with clay, and after giving force, the shape is changed, but after removing force, we cannot get the original shape of the clay. So this is also in elastic ball. Now, an elastic collision loses no energy. The deformation on collision is fully restored, but in an inelastic collision, energy is lost and the deformation may be permanent. So this is the real life example. Now, an elastic spring. A spring is an example of an elastic body that can be deformed by stretching. But if we apply force, then the length of the spring will be increased. Suppose this is the x increase here, and a restoring force F, that means applying force, acts in the direction opposite the displacement of the oscillation body. That means F equals to minus kx, because my negative sign indicates what? Actually, the when the spring is stretched, there is a restoring force that is proportional to the displacement. Actually, this is actually Hooke's law. You must know about the Hooke's law. The spring constant K is property of the spring given by this. That means K equals to, can be written by change in force divided by change in length. This is the ratio. And the spring constant K is a measure of the elasticity of the spring. So now, what is the stress? Stress refers to the causes of a deformation, and strain refers to the effect of the deformation. So the downward force F causes the displacement X, and thus the stress in the force, stress means pidon, you must know pidon, and strain means bikriti. Okay, so the stress is the force and strain is the elongation. Elongation means bikriti. Okay, strain means bikriti. So there is a x strain, but F means this force, that means stress. So types of stress, the tensile stress occurs when the equal and opposite force are directed away from each other, and this is the actually tension, and weight W and force F is applied here, then the tension occurs. Now, a compressive stress occurs when equal and opposite force are directed towards each other. That means this will be equal and opposite. Compression, after compression, chap delay, compression created, then equal and opposite. Now, stress is the ratio of the applied force to the area over which it acts. That means the stress equals to force, applying force per unit area of a body, and its unit is Pascal. Okay, so strain means, Vikriti means what? Is the relative change in the dimension or shape of a body as the result of an applied force. If we apply any force on a body, then it will become change in length, change in area, change in volume, etc. Okay, so example, change in length per unit length, change in volume per unit volume. Okay, so longitudinal stress and strain, Durgo Vikriti or Durgo Pidam. Okay, so for wire rods and bars, there is a longitudinal stress F by A that produces a change in the length per unit length. In such cases, we can write the formula for stress F by A and strain. Strain means Vikriti, change in length divided by the original length. Okay, the stress means what? Applied force divided by per unit area. Now, this is the example for finding the stress. Okay, original length was L, but the change in length del L. Then first find the area of the air. So this is the pi d square by 4, area equals to, that means d means diameter, and diameter is given. So area equals to this. This is the, and the stress will be force per unit area, and this will be the result. 6.37 into 10 to the 7 Pascal. Now another example. This is also finding the strain and longitudinal strain. That means Durgo Vikriti will be this. Another one, what is elastic limit? The elastic limit is the maximum stress of a body can experience without becoming permanently deformed. That means, and stress means per unit force per unit area, and weight is W here. So original length was 2 meter. Then if we apply 2 times weight, that means force, if the stress exceed the limit, elastic limit, the final length will be longer than the original 2 meter. Okay, so this is okay, but beyond limit, it cannot be possible to maintain the original limit. Okay, the ultimate length is the greatest stress of a body can experience without breaking the repulsion. Okay, so original length was 2 meter, but after applying force F, we get the stress, but to more and more giving force, it will limit the cross. This is why এটা ছিঁড়ে যাবে, ছিঁড়ে গেলে যে ফোর্স অ্যাপ্লাই এর পর এটা ছিঁড়ে যাবে, সেই ফোর্সটার নামই হচ্ছে actually limit. If the stress exceeds the ultimate strength, the string breaks. That means this is the actually real life example for finding the elastic limit. So elastic limit equals to this. Okay, 779 Newton is the limit. Another example, similar example, we recall the area and also stress. So this is 1536 Newton. This is the elastic. Now what is the modulus of elasticity? So the provided that the elastic limit is not exceed and elastic deformation means a strain means vikriti is directly proportional to the magnitudes of the applied force per unit area, that means stress Pidon. So modulus of elasticity equals to ratio of stress and strain, that means vikriti divided by Pidon. Pidon divided by vikriti is called modulus of elasticity, and this is the example for finding the modulus of elasticity. And this longitudinal modulus of elasticity is called Young's modulus, okay, and is denoted by the symbol Y. So Young's modulus equals to, you write longitudinal stress, that means Durgo Bikriti divided by Durgo Pidon. So this is the formula for finding. This is the formula for stress in longitudinal, and this is the strain Bikriti. So this is the formula for finding Young's modulus, and unit will be Pascal. Similarly, you can find out the Young modulus by using this formula. Similarly, another example for finding the increase in length 0.605 millimeter. And what is the shearing stress? Partial pidon. Okay, partial বিকৃতির কারণে যে পীড়ন হয় তাকে shearing stress or partial pidon বলা হয়. Shearing stress alters only a shape of the body, leaving the volume unchanged. For example, consider equal and opposite shearing force acting on the cube. This is a cube. So after a shearing stress, it change in angle with an angle pi and length in small l, and after giving force, so the distance is d, then the stress is given by F by A. So calculating shearing modulus in this case, stress in the force per unit area, you must know the formula. Stress equals to force per unit area, F by A. The strain is the angle expressed in radian. Radian means was angle, and this is the diameter, d divided by L. The change in length divided by original length, strain. So shear modulus S is defined as the ratio of the shearing stress divided by shearing strain. That means partial pidon divided by partial বিকৃতি কে বলা হয় partial modulus, that means shearing modulus. So the shearing modulus units in also Pascal. Now this is the example for finding the shearing stress and shearing modulus. This is the diameter increased in length 0.022 meter. Now volume elasticity. Now all of deformation are linear. Sometimes one can apply force per unit area in the decrease of volume or increase of volume. In such case, we have to use the volume elasticity. This is also called bulk modulus B, and this is given by volume stress divided by volume strain. That means ayaton pidon divided by ayaton vikriti. The ayaton pidon will be negative because volume, after giving pressure on a specific body to the volume of body will be increased, sorry, decrease. This is why negative sign here. And the bulk modulus is negative because of decreasing in volume. Okay, so what is the bulk modulus? This is the formula for finding bulk modulus. Then aeton freedom divided by aeton vikriti. So force per unit is generally pressure. We may write this unit will be same as longitudinal modulus, sharing modulus. So same. So this is the example for finding bulk modulus of a body, and decreasing in volume indicate the negative sign. Similarly, this is the summary we have. This is the summary types of stress. Okay, and this is the formula we have used. Stress means pidon, and this is the formula we have used. Longitudinal stress and longitudinal strain, and we have also discussed about the elastic limits, and this is the formula for Young modulus, and this is the shear modulus formula, and this is the for bulk modulus. So so we have discussed about this what is longitudinal strain, that means Durgo Bikriti. Okay, shearing strain, we have also discussed this, and elastic limits. And we must know about the what is the Hooke's law. This is the stress divided by strain. It will this ratio will be a constant. This is called a Hooke's law, and this is the formula for finding Young's modulus of elasticity. Okay, normal stress divided by longitudinal strain. Okay, force per unit area is called stress. Stress means pidon, and strain means Bikriti. Okay, this is the modulus of rigidity, tangential stress divided by shearing strain. So this is the formula for bulk modulus, okay, of elasticity. And we also discuss about the now determination of Young's modulus by Charles method. So this is the a method for finding the Young's modulus. And suppose there is a wire suspended and a weight is attached to it. So the wire A is loaded, and its length increase. The free end of the spirit level moves down. The head of the speedometer is rotated to bring the spirit level to the horizontal position. So in this case, stress equals to force per unit area. Area means A, and this is the circular area. This is a pi r square. And F equals to mg. This actually force will be weight mg, and strain will be increase in length divided by original length বিকৃতি দৈর্ঘ্য পরিবর্তিত দৈর্ঘ্য divided by আগের দৈর্ঘ্য. So Young modulus will be this, and the value of m by L is obtained from the graph. The load applied should not more than the elastic limit of the air. The elastic limit depends upon the nature of the material and radius of the air. So this is the Young modulus. Now, why glass is more elastic than rubber? We can actually explain this. Glass is more elastic than rubber because it is a given stress. The strain produces in a glass in mass less than that in rubber. Suppose for the rubber, Young modulus yn equals to FL divided by L1. In that case, for glass, Y2 equals to FL divided by L2. For two materials, force, length, and area remaining the same, but the increase in length for the first body L1 and for rubber, and is more than the the increased length L2 for the glass. So Y2 is greater than Y1 here. Actually, we can yield point, elastic limit, and elastic fatigue. Okay, what is elastic limit? We have discussed it. And what is elastic fatigue? স্থিতিস্থাপক ক্লান্তি, elastic fatigue. If a body is continuously subjected to stress and strain, it gets fatigued. That means এটা পূর্বের অবস্থায় আর ফিরে যায় না, একটু চেঞ্জ হয়ে যায়, সেক্ষেত্রে এটা পূর্বের অবস্থায় ফিরে যেতে অনেক সময় লাগে। Consider two torsional pendulums and B having similar wares. A is initially set to vibration. After A has come to rest, both the pendulums and B are set into vibration continuously. It will be found that due to the elastic fatigue, A comes to rest earlier than B. And this is the calculation for finding bulk modulus. We have discussed these types of. Calculate the density of a lead. Lead means shisha. After a pressure, this Pascal, density of lead will be this bulk modulus. We know the bulk modulus K equals to, this is the formula, and M equals to B rho. So mass equals to volume multiply density. So differentiating, we get this, and we can calculate the density under the pressure. So this is another example. A horizontal steel of wire length L meter and area of cross section will be 10 to the power minus 6 meter square is stressed between two fixed supports. We have to calculate the Young modulus for that. That means here T by L equals to mg by twice x. That means 2 times increase. So this is why in the first case T1 divided by L1 equals to this one. So T1 equals to, and similarly T2 equals to same formula, and the increase in length, first length will be this. So change in strain and change in stress. So we get the Y as a Young modulus. Now Poisson ratio, we must know what is Poisson ratio. The longitudinal strain per unit stress, and beta is the lateral strain per unit stress within the elastic limit. So beta divided by sigma A. So Poisson's ratio equal to beta divided by A. Therefore the Poisson's ratio is defined as the ratio of the lateral strain partial pidon divided by partial vikriti equal to Poisson's ratio. Now consider a wire of length L and diameter D. The wire is fixed at one end point and force is applied to another point. Frequently the length of the wire increased and the diameter of the wire decreased. So diameter will be decreased due to pressure. This way increase in length will be is dl, and increase in diameter dt. So decrease in diameter dt. So Poisson's ratio equals to increase in diameter divided by increase in length. So this is the actually calculation for Poisson's ratio. The value of the Poisson's ratio mainly depends upon the nature of the materials of the body. So sigma, that means Poisson's ratio has no units because it is the ratio of two numbers. And for most substance, the value of this lies between 0.2 and 0.4. Now, initial volume of the air will be equals to this, and differentiating, we get dB equals to 0. So for the maximum, derivatives will be 0, first derivative. So this equals to, we get, so sigma equals to half. That means the maximum possible value of Poisson's ratio is half. Now Poisson's ratio of a rubber, we can calculate this Poisson's ratio. Okay, so similarly differentiating and subject to the value of dA, we get the Poisson's ratio for sigma rubber. Now work done in deforming of a body. So for work done, a longitudinal strain, I consider a wire of length L, area of cross section A, and Young modulus of elasticity Y, and L be the increased in length when a stretching force F is applied. Therefore work done will be 0 to L. That means increasing length. This is the force, applied force, and this is the increased length. But we know Young modulus equals to F divided by L by L. So F equals to this, just putting the values here, we have to integrate 0 to L. So integration will be half FL. Work done per unit volume equals to what will be? W by B. And volume equals to what? Area multiply length. Okay, L. This is why work done equals to what? What was half FL. This is why we get W equals FL divided by twice L. Half F by A, L by L. But F by A, force per unit area is stress, that means speed on, and L by increased length divided by original length will be strain, Vikriti. Similarly, we get this equation for shearing strain also. Consider a cube of L when tangential force is F is applied, then and shearing angle will be pi. If the tangential stress is capital T, then eta equals to shearing strain equals to share tangential force divided by pi. T equals to this one. Total tangential force will be T capital T A. Okay, total. And this tangential force will be for per unit area. This is why total will be TA. Eta A pi. Work done will be F dl, increase in length. Here dl equals to L d pi. So work done will be, so we get this. So work done in per unit volume will be this. Volume means what? L. This is why similarly we get for tangential force, half strain equals to strain. This is the shearing for shearing stress. Similarly, for volume strain, we can also calculate the work done. Consider a cube of a volume B, area of a cross section A, and length L. When a normal stress P is applied, the change in volume will be B. So work done will be 0 to B, P dB. K equals to what? For a strain volume, will be this, and but K equals to PV by B or P equals to KB by B. That means just similarly we can get the same equation. So work done per unit volume will be this. That means also half stress strain. Similarly, we can solve some real life examples and find out the Young modulus per unit volume, which can be stored in the metal when stressed. So this is given Young modulus, maximum stress is this. So energy stored in per unit volume, we have derived this formula. So just putting the values, we get the result. Similarly, we can find out also the work done, and we also same joule work done. Unit will be joule. Now relation between eta, y, and sigma. Let alpha and beta be the longitudinal and lateral strain per unit stress respectively. Extension along diagonal AC due to the tangential stress. That means T A AC. Okay. Sigma is the area. There is also lateral extension along AC due to the compression stress T capital T along the diagonal BD. It is equal to the T beta AC. So total will be just adding to these two. Similarly, we get this total will be this, and pi equals to small l by capital L. This is why pi equals to twice T alpha plus beta. So eta equals to us capital T divided by pi. That means just using this relation, we get 1 divided by 2 alpha plus beta. Hence eta equals to 1 by 2 into alpha plus beta, and eta equals to 1 by twice alpha 1 plus sigma. So, but 1 by a equals to y, and similarly we get the eta equals to this one. Now relation between elastic constant, various equation can be equations are Young modulus this, and bulk modulus this, and this is the volume. So from equation 2 and 3 we get this equation. Adding 4 and 5 we get this relation 6. Now from equation 6 eta equals to this. Similarly y equals to this, eta equals to this one, and k equals to this. Now from equation 7, 8, 9, values of eta, y, eta, and k can be calculated in two values are known. So it equals to 1 by half 1 by 2 into alpha plus beta. Just taking common alpha, we get this beta by alpha. Eta equals to this and this. Multiplying equation 4 by 2 and subtracting it from equation 5, we get 6 beta equals to this. That means beta equals to this one. And the relation for Poisson ratio can be found in terms of eta. Poisson ratio equals to beta divided by alpha. That means beta y. 1 by alpha equals to y. So just putting the values, we get sigma. So this is the relation between sigma eta k. Okay. And this is the example for finding the value of Young modulus of the material of the air. Another example, you can calculate just using the formula. This is also another formula. This is the uniform rod, an example for you. So this is another example, calculating the additional load, that means force, that will be required to restore the length of the wire. We have to calculate weight, kg per unit weight. This is also called Newton. And this is another example for the longest length of steel, stress of the air. This is the formula. This is also Poisson's ratio formula. A twisting cylinder. For a twisting cylinder, this is the one upper part or lower part of a cylinder. This is the thickness dx, and this is the center c, and this is the b, and after rotating theta, there will be b dash, bulk modulus. So bb dash equals to x theta l pi, pi equals to this one. So pi is the maximum at the rim and 0 at the axis. Shearing stress will be capital T, it equals to T by pi. So capital T equals to this, and area of the cross section will be 2 pi x dx. This is the area. 2 pi x means what? Actually circumference of the circular portion, and this is the actually thickness dx. This is why area. So shearing force on the shell will be capital T per unit area. That means capital T into area. So total shearing force. So if F equals to, just putting this equation, moments of this force about the axis OC will be this one. So total twisting couple for the whole cylinder will be this. Let the couple per unit twist be C. So tau equals to C theta. Comparing 1 and 2, we get C equals to this one. So the couple per unit twist is C, is also called the torsional rigidity of the material of the air. Now hollow cylinder, for hollow cylinder, we get this one. In the special case, we can also observe that the larger twisting couple will be required in case of the hollow cylinder as compared. Now, very important part, cantilever. A cantilever is a thin uniform bar fixed horizontal at one end and located at the other end. Let A be represented this. This is the actually area, and this is the radius, and PQ, this is the actually second. So theta between angle the PQ, and this is the B dash, and this was the original bulk modulus, and this is the B dash after sharing. So natural axis of the cantilever of length L, and the end A is fixed and B is rounded with a load W vertically downwards. So in that case, bending moments will be YL now divided by R. Deflecting couple W equals to L minus X. For equilibrium, this load will be equal, and there is actually differential, but 1 by R equals to d square y by dx square. So d square y by dx square equals to this. Integrating, we get first derivative and this integration with respect to x. So this is the k1 is the actual integral constant. If x equals to 0, then we get this one, and integrating equation will be, and if x equals to y equals to 0, we can calculate that k2 equals to 0. So we can easily get the y equals to this. This is the depression of the free end for the x equals to L. So circular cross section, we get this. And for heavy cantilever, we can calculate similar way. This is the for heavy, and this is the integrating to after integrating twice. This is the beam for the heavy load, and at C point the load is suspended, and this is the half minus Lx, and this is the L minus x. So this at equilibrium point we get this, and 1 by r equals to this one, but again 1 by r equals to d square over dx square. So just a differential equation, second order. So we similarly we get C1 this, and substituting we can, so this is the actually calculation for the beam of a circular cross section. So this calculation so this is the actually